When you read a staggering statistic, sometimes it just completely stops you in your tracks.
Oh, definitely.
Yeah, and here is one for you from our stack of sources today. Nearly 3 in 4 women will experience painful sex, which is clinically known as dyspareunia, at some point in their lives. I mean, 3 in 4.
It really is a massive number, and, it is one of those completely ubiquitous human experiences that, well, for whatever reason, remains shrouded in so much silence and just embarrassment.
Yeah.
People just sort of assume it's an inevitable part of aging or maybe postpartum life that they simply have to endure.
And that is exactly what makes today's deep dive into the source material so important.
Mm-hmm.
Because for you, the listener who loves digging past the taboo and into the actual, mechanics of a problem,
Mm-hmm.
we're going to look at this in a completely different light.
Yeah, we really are.
We aren't just looking at a medical complaint here. We're looking at a fascinating, highly complex problem of biomechanics and biophysics.
We have a really unique stack of sources to guide us today, too.
We do.
We're pulling from clinical medical blogs on female sexual health, some really deep-cut rheological studies.
There's the physics of how liquids and gels flow, right?
Exactly, specifically focusing on dermal fillers in this case. And finally, some highly advanced biomechanical research on the structural dynamics of pelvic floor muscles.
It is a true cross-disciplinary stack, and our mission for this deep dive is incredibly specific.
Very targeted today.
We're going to uncover exactly how a specific mathematical property, the elasticity modulus, known in physics as G prime,
Right, G prime.
how the G prime of high viscosity cross-linked hyaluronic acid acts as a microscopic shock absorber. We want to figure out how this specific property prevents a gel from just flattening out under the intense friction of sex, and how it ultimately rescues the anterior vaginal wall.
It's quite the journey.
Okay, let's unpack this. We really have to start by understanding the battlefield itself. Why does the vaginal wall suddenly need mechanical structural help in the first place?
Well, to understand the structural failure, you first have to look at the project manager of the whole vaginal environment, which is estrogen.
Oh.
Estrogen is the hormone responsible for maintaining that local ecosystem. It signals the body to keep the tissue lubricated, it maintains elasticity, and it essentially keeps the vaginal walls thick and robust.
So they're basically telling the cells, hey, keep producing the good stuff, keep everything plump and protected.
That's a really good way to look at it. But estrogen levels aren't static.
Right.
When those levels drop significantly, which happens naturally during menopause or postpartum, especially while breastfeeding.
Or even due to certain cancer treatments, right?
Exactly. The tissue undergoes a process called vaginal atrophy. Without estrogen giving the orders, the biological infrastructure essentially just starts to shut down.
So walls literally become thinner, they dry out, and they become highly prone to inflammation.
Right. But let's zoom out for a second and look at the larger structural support system of the normal pelvic organs, because it relies on an incredibly delicate balance of forces.
Okay, lay it out for us.
You have the levator ani muscles. These act like a sling that holds the pelvic floor closed. And by keeping that area closed, they create a high-pressure zone inside the abdomen, much like how a sphincter keeps things contained.
So the muscles are providing the floor.
Yes. And then you have the suspension system above that. You have ligaments, specifically the cardinal and uterosacral ligaments, providing lifting forces. They actively resist the downward descent of the organs.
Okay, I see. So when everything is healthy and working, the muscles keep the opening closed from the bottom, and the ligaments absorb any sudden spikes in pressure from the top, like when you cough or laugh or lift something heavy.
Exactly. But now introduce the atrophy we just talked about. When those tissues thin out and that natural thick layer of lubrication drops, the environment fundamentally changes.
It's totally compromised.
Yes. If you introduce coital penetration into that compromised environment, you're suddenly introducing an intense, repetitive amount of friction directly against highly vulnerable tissue.
It's like a high-performance engine suddenly running completely without motor oil.
That's exactly what it's like.
The pistons are just grinding against the cylinders.
Yeah.
And that friction doesn't just cause a little bit of heat or irritation, right? It causes actual physical deformation of the tissue under load. It pushes those delicate, thinned-out tissues completely out of alignment, leading to severe pain.
Yes, either superficial entry pain right at the vulva or deep mechanical pain inside the vagina.
Right.
And the physics of that mechanical failure are actually staggering. When you have that deformation under load and the thinned, compromised muscles fail to hold that high-pressure zone closed, the vaginal walls can physically descend or bulge.
Oh, wow.
Yeah. This misalignment creates a literal pressure differential between the heavy abdominal cavity and the atmospheric pressure outside the body.
Wait, a pressure differential, meaning the abdomen itself is literally pushing down on this raw, exposed tissue.
It is a massive amount of downward force. If the anterior vaginal wall, so the front wall, misaligns, abdominal pressure pushes down on it like gale force winds filling a ship's sail.
That sounds intense.
It is. The larger the exposed area of tissue, the greater the force compounding on it.
I think for anyone listening, trying to visualize that, it's hard to grasp just how much internal pressure we carry around on a daily basis.
To give you some context from the biomechanical sources, let's look at a Valsalva maneuver.
Okay?
That's the medical term for forcefully bearing down, like when you cough deeply or strain. If you generate 100 centimeters of water pressure during a cough and apply that to just 1 square inch of exposed misaligned vaginal tissue,
Yeah.
that results in almost 1.5 pounds of downward force on that single square inch.
A pound and a half of force hitting a tissue that is already thinned out, dry, and inflamed from a lack of estrogen. I mean, that just sounds agonizing.
It severely exacerbates the tissue damage. It places abnormal stretching tension on those suspensory ligaments we talked about, and it magnifies the deep pain pathways. It really becomes a vicious cycle of structural failure.
So if there's literally a pound and a half of downward force crushing this raw tissue, throwing a simple moisturizing cream at the problem feels like, I don't know, bringing a Band-Aid to a structural building collapse.
It really is.
It's a purely mechanical problem, kick-started by friction. So if estrogen isn't an option for a patient, say maybe they have a history of breast cancer and they literally can't take hormones, how do you physically prop that tissue back up? Like, how do you build a microscopic shock absorber for the human body?
That is exactly where we turn away from hormones and look toward bioengineering, specifically the engineering of hyaluronic acid, or HA.
Okay, I know a lot of our listeners are probably familiar with HA from their skincare routines. I mean, it's in every single serum and moisturizer on the market right now.
It is, yeah. But the HA we are talking about here is a completely different beast than what you rub on your face.
Okay, how so?
Biologically speaking, HA is a naturally occurring glycosaminoglycan. It's a vital foundational component of the extracellular matrix in almost all adult animal tissues.
So it's already everywhere.
Right. It's in your skin, it lubricates your joints, it's even what gives the vitreous body of your eye its shape. Its primary biological job is to bind to water, hold moisture, and provide structural volume to tissue.
But okay, if it's already in the body, why can't a doctor just take some natural HA, inject it into the vaginal wall to give it volume, and call it a day?
Because your body is highly efficient at cleaning house.
Oh, interesting.
Yeah, if you were to inject native, naturally occurring HA into the tissue, it would be rapidly destroyed by your body's own hyaluronidase enzymes.
Hyaluronidase enzymes.
Exactly. These enzymes act like little molecular scissors, constantly chopping up and recycling HA. Native HA only has a half-life of about 12 to 24 hours in the tissue before it vanishes completely.
Oh, wow. So injecting natural HA would be totally pointless for long-term structural support? It would just dissolve overnight.
Precisely. To make HA survive as a durable, therapeutic implant that can actually withstand physical pressure, it has to be chemically engineered in a lab. It has to go through a process called cross-linking.
Cross-linking. Walk me through this, because if we're injecting this into some of the most sensitive tissue in the human body, the idea of adding chemical agents to modify it sounds, well, like a potential red flag. What are we actually doing to the HA?
It's a very tightly controlled chemical process. Think of native HA as millions of individual floating strands of spaghetti.
Okay.
What bioengineers do is introduce a cross-linking agent, and the most common one in our sources is called BDDE.
BDE.
Right. You don't need to memorize the chemical name, but think of BDDE as a series of... That's a great visual, yeah. By tying these strands together into a 3D network, the engineers are building a steric barrier. It's basically a physical maze.
Right.
Now, when those hyaluronidase enzymes, molecular scissors, come along to chop up the HA, they can't easily navigate the maze to break the bonds.
Because it's all tangled up.
Exactly. The HA becomes incredibly resistant to breaking down, meaning it can survive in the body for months or even over a year.
But wait, going back to the safety aspect, you are using a chemical anchor to tie these molecules together. Is that really safe to leave inside the body?
It's a very valid concern, and it's something the FDA heavily regulates. The cross-linker, BDDE, can have slight mutagenic risks if it is left floating around unreacted in the gel.
Okay, that sounds bad.
It would be. So the manufacturing process includes aggressive purification steps to wash away any of those loose chemical anchors. The FDA strictly requires that any residual unreacted BDDE be kept under 2 parts per million.
2 parts per million. That's tiny.
To put that in perspective, that's less than 0.0002 milligrams of residual chemical per milliliter of gel.
Wow.
Yeah, it is an infinitesimally small trace amount, ensuring the gel is exceptionally safe and biocompatible.
Okay, so we've safely built this highly durable, cross-linked HA gel. It won't dissolve. But how does that structural net translate to the actual physical feel of the implant? I mean, if we are tying all these molecules together into a tight web, doesn't it just turn into a hard lump of plastic under the skin?
Not at all. And that's where the true art of the bioengineering really comes in. The density of those crosslinks dictates the rheology of the
A
gel.
rheology, right? How it flows.
Exactly. Rheology is the branch of physics that studies how materials flow, how they deform, and how they bounce back under pressure. By carefully controlling how many chemical anchors are used, scientists can elevate the concentration of the cross-linked HA just enough to increase its structural elasticity without losing its pliable, tissue-like nature.
Okay, so we have a pliable, durable gel. But now we have to deploy it into one of the most mechanically stressful environments imaginable. We are talking about the intense, repetitive friction of sex.
Right.
If you put a glob of gel between two surfaces that are grinding together, natural logic just says the gel is going to flatten out, get pushed to the sides, and become totally useless. How do they engineer this gel to survive coital friction without just pancaking?
This is the crux of the entire biomechanical solution. To prevent the gel from flattening, the engineers rely on one highly specific mathematical property. And to understand it, we need to look at how rheologists test these materials in the lab. They use something called oscillatory strain amplitude tests.
Oscillatory strain amplitude test. That sounds incredibly dense.
It's actually quite simple conceptually. Imagine placing a dollop of the gel between two metal plates and then rapidly sliding the top plate back and forth to simulate friction and shear force.
Okay, I can picture that.
The machines measure how the gel behaves under different frequencies and pressures. These tests give us a few key parameters. The big overarching one is called G-star, or the complex modulus.
So think of G-star as the total overall toughness of the gel.
Right. G-star is the total rigidity. But that total toughness is actually made up of two distinct competing personalities within the gel.
Competing personality.
Yeah, the first personality is G double prime, known as the viscous modulus.
Viscous, meaning liquid-like honey or syrup.
Exactly. G double prime represents the liquid-like behavior of the gel. It's a measure of how much mechanical energy is actually lost to internal friction when the gel gets squished. If a gel has a high G double prime, it behaves more like a liquid. When you remove the physical stress, it lacks the ability to completely recover its original shape.
So a high G double prime gel would be like pancake batter. If you press down on it, it spreads out, but when you lift your hand, it just stays flat.
Exactly. And the second competing personality is G prime, the elastic modulus.
Ah, the star of the show.
Yes. This represents the solid-like behavior of the material. G prime measures the mechanical energy that the gel actually stores inside itself during deformation, which it then uses to instantly regain its original shape once the pressure is gone.
Okay, here's where it gets really interesting, because I think the terminology here can trip people up. In everyday life, if you hear the word viscous, you think thick and protective.
Right, you do.
But in this biomechanical battlefield, viscous is actually the enemy. We do not want a gel with a high G double prime acting like pancake batter, because the lateral friction of penetration would just permanently flatten it or displace it.
You've hit the nail on the head. A viscous gel would be useless here. During intercourse, the anterior vaginal wall isn't just taking downward pressure, it is subjected to intense lateral shear forces. That side-to-side coital friction would completely destroy a viscous gel's shape.
So we need the opposite. We want something engineered with an incredibly high G prime. We want it to act less like pancake batter and more like a microscopic memory foam mattress, taking the hit from the friction and bouncing right back.
Memory foam is close, but let's take that analogy one step further, because memory foam actually takes a few seconds to rebound. This high G prime gel has to snap back instantly, in fractions of a second, over and over again. It's really more like injecting a microscopic trampoline.
A microscopic trampoline, that perfectly visualizes it.
Yeah, when you'd inject a high-viscosity, cross-linked HA that is designed specifically to maximize that G prime elasticity modulus, it behaves almost entirely elastically under stress.
Okay.
When the lateral shear forces of coital friction hit it, the gel absorbs that mechanical stress. It physically deforms for just a millisecond, stores all that energy, and then immediately springs back to its original three-dimensional shape. It never flattens out.
That is wild. So by retaining its shape against the friction, this high G prime gel is effectively replacing the lost mechanical protection of the youthfully thick vaginal wall.
Yeah.
It is stepping in for the estrogen that went missing.
It acts as an unbreakable mechanical shield because beneath the surface of the vaginal wall is the lamina propria, which is a layer of connective tissue that is absolutely packed with nociceptive pathways.
Nociceptive pathways, those are the nerve endings that sense pain, right?
Exactly. When the tissue is thin from atrophy, the friction grinds directly against those nerves. But when you insert this high G prime HA shield, it provides a durable, bouncing cushion that absorbs the shear force before it can ever reach the pain receptors.
It really is brilliant engineering. We've effectively solved the biological friction problem using physics instead of hormones.
We have.
But here is the thing. The vaginal wall isn't just an inert plastic tube that needs structural scaffolding. It is a living, breathing organ made of contracting muscle.
Yeah.
If we inject this highly elastic gel into the tissue, how does that structural implant interact with the actual cellular function of the muscle itself? I mean, does the body fight it?
To understand that, we need to look at the muscle tissue itself. The vaginal wall is supported by vaginal smooth muscle, or VSM. Now, smooth muscle generally comes in two operational modes in the body. You have tonic muscles, which hold a slow, sustained, continuous contraction, like the muscles regulating your blood vessels.
Right.
And you have phasic muscles, which contract rapidly and rhythmically.
Like your intestines digesting food or the uterus during childbirth.
Exactly. The vagina relies heavily on phasic contractions. These rhythmic contractions are absolutely vital for sexual arousal, for accommodating childbirth, and even for assisting the pelvic floor in maintaining urinary continence.
Okay.
And the biomechanics research from our sources shows that these contractions are incredibly complex at a cellular level.
They are governed by cellular electrical signals,
Right.
right? Like the flow of calcium ions.
Yes, exactly. Voltage-dependent calcium channels dictate the influx of calcium ions into the muscle cells, which acts as the spark triggering the muscle to contract. But what researchers found when they looked at this in lab models, specifically rat and marine models, is something totally wild.
What's that?
The vaginal tissue doesn't just contract uniformly like a simple rubber band. It is highly anisotropic.
Anisotropic, which is a scientific way of saying it reacts completely differently depending on the direction of the force you apply to it. Like a fabric that stretches easily side to side, but is super rigid top to bottom.
That's a perfect way to translate it. The researchers proved this by stimulating the tissue in two different ways. First, they shocked the tissue with an electrical field. This electrical stimulation caused the muscle to contract heavily in the circumferential direction.
Meaning it's squeezed inward around the tube of the vagina.
Right. But then they used a chemical trigger, applying potassium chloride. This chemical signal caused the muscle to contract completely differently, generating higher stress in the longitudinal direction, pulling along the length of the vagina.
Wow. So it's this incredibly dynamic, highly directional living environment. It is constantly shifting, pulling, and responding to different signals.
Very dynamic.
So what happens to that living ecosystem when we inject our bouncy high G prime HA filler into it? Our sources highlight clinical treatments, like the Zerial Plus, which are injected directly into the labia majora and the vulvovaginal area. It can't just be taking up inert space, right?
It definitely isn't just taking up space, and this is where the physics and the biology beautifully intersect. By inserting this HA, you are restoring the physical volume of the extracellular matrix. And because HA is a moisture magnet, it rehydrates the tissue from the inside out.
Makes sense.
But more importantly, the physical presence of this highly elastic gel triggers something called biostimulation.
Biostimulation, meaning it tricks the body into waking up.
Exactly. The mechanical presence of the gel, physically stretching the fibroblasts in the tissue, actually prompts the surrounding cells to start increasing their native production of collagen and elastin again.
Oh, wow. So what does this all mean for the listener? It's like we aren't just spackling a crack in a foundation to keep the water out. We are inserting a smart scaffold.
A smart scaffold, yes.
We put the scaffolding up to bear the load, but the scaffolding itself actually tells the surrounding cells, hey, wake up, start manufacturing your own bricks and mortar again.
That framing is absolutely spot on. It's a dual-action therapy. It's a passive mechanical shield against friction on day one, but it becomes an active biological regenerator over the following months. And if we connect this to the bigger picture of the pelvic floor, remember that normal, healthy vaginal smooth muscle maintains a basal tone.
A basal tone. So just a continuous low-level tension, like the resting tension of a guitar string.
Right, just enough tension to maintain the anatomical shape of the organ. When you have severe atrophy and volume loss, that anatomical balance is totally destroyed. The muscle is stretched, you get abnormal tension, and you get those massive pressure differentials from the abdomen pushing down that we discussed earlier.
The 1.5 pounds of force per square inch.
Yes. By inserting this highly elastic, biostimulating filler, you physically restore the anatomical contour of the tissue. You prop the wall back up, which instantly relieves the abnormal tension on the surrounding pelvic floor muscles.
That's huge.
It is. This physical support allows the vaginal smooth muscle to relax back into its natural basal tone without being constantly overstressed and stretched out of alignment by abdominal pressure.
It's an incredible cascade of therapeutic effects, really, all starting from a single engineered property.
Yeah.
Let's take a step back and sort of summarize the journey we've been on in this deep dive.
Sure.
We started with an incredibly common yet rarely discussed issue, which is painful sex, largely caused by the drop in estrogen, which leads to vaginal atrophy, thinning tissue, and intense mechanical friction.
Right.
We then zoomed all the way down to the microscopic molecular level to see how the bioengineering of hyaluronic acid solves this.
Specifically, the cross-linking of HA with BDDE to create a spheric barrier against enzymes.
Exactly. And most importantly, we uncovered how the elasticity modulus, the G prime of that cross-linked HA, allows the gel to act as a resilient microscopic trampoline. It instantly bounces back from the lateral shear forces of coital friction, completely preventing the gel from flattening in the anterior vaginal wall.
It really is a marvel of physics.
And in doing so, it acts as a mechanical shield against pain, while simultaneously triggering the living tissue to begin healing itself through collagen biostimulation.
It really highlights how interconnected the physics of a material are with the biological healing of the human body. But, this raises a very important, highly provocative question when you look at the long-term implications of this science.
Oh, I like where this is going. Leave us with something to think about.
Well, if highly engineered high G' hyaluronic acid can successfully mimic the extracellular matrix to the point where it fundamentally alters abnormal muscle tension and stimulates new collagen and elastin production, what is the limit of that therapy? Could regular, preventative, non-hormonal filler treatments eventually teach the vaginal smooth muscle to permanently recover its own basal tone?
Oh, wow.
If we catch the mechanical failure early enough, before the ligaments give out, could what started as a cosmetic, anti-aging dermal filler tool actually become a permanent preventative cure for pelvic organ prolapse before the prolapse even begins?
That is a fascinating possibility. The idea that engineering the perfect microscopic bounce could permanently reverse a major structural collapse in the body. It is a perfect reminder that sometimes the most profound medical breakthroughs come from just understanding the microscopic physics of how our tissues actually work. Just something for you to mull over. Until next time, keep diving deep.